So we continue to discuss spectral theorem. As I say, the main idea of spectral theorem that any self-adjoint operator is similar to multiplication operator. So theorem, but not theorem, definition. Let X is Banach space. A is maybe not bounded linear operator. And vector x0 is cyclic if linear span of powers, all powers, is dense in our space X. So if so-called orbit, positive orbit of vector generates all space, but linear span. Example. Some examples. Of course, we study situation in Hilbert space because we will work with self-adjoint operator. But this definition is valid for arbitrary operator. Examples. Let's consider Cn, and operator A is diagonal operator, maybe complex numbers, so it's not obvious self-adjoint operator. But I state that for this operator exists a cyclic vector if and only if all lambda g are different. So there exists cyclic vector if and only if lambda e is not coincide with lambda g, if I is not equal to g. Why? One situation. Let first lambda I is not equal to lambda g, then I state that I can take x0 as 1, 1, 1. Why? Because if I take powers a k x0, k from 0 to n minus 1, we have n-dimensional space. N-dimensional space. And if you consider these vectors, it's easy to see that determinant of these vectors, determinant, is so-called van der Monde determinant. Is it no motion van der Monde determinant? Yes. Van der Monde. Van der Monde determinant. It is not zero due to this assumption. So they are linear independent. So all these vectors are linear independent, so it is basis in space. So it is dense, yes. So linear span is gives us all space, because it is without any closure, because it's finite dimensional situation. Yes. So it is basis, because it is not zero. But if second, let we can do it by changing of numeration, yes. So then it's easy to see that the minimal polynomial which annihilate our operator, our matrix, have power less than n minus, less or equal n minus 1. So you can see that if you take this polynomial, for example, p of lambda, lambda minus lambda 1, lambda minus lambda 3, lambda minus lambda n. I miss special lambda minus lambda 2 because they are equal. So if we take p of a, it equals to 0 because this bracket vanish these two elements. So and this is polynomial is power degree, so it is equal lambda n minus 1 and so on. Yes, degree of this polynomial is n minus 1. So is with some constant, okay, c1 lambda n minus 2 plus and so on. Then you see that p of a equals to 0. Then you see that a minus 1 equals minus c1 a n minus 2 minus and so on. So this power is a linear combination of these powers, of the less powers. So you can't obtain all space. They are linearly dependent. Linear dependent. So you have less or equal n minus 1 linear independent vectors. It was first example. Second example, infinite dimensional situation. Infinite dimensional situation. Let's consider L2 minus 1, 1. So it's example 2. And consider operator of multiplication on x square. It is, of course, self-adjoint operator. And I claim that this operator have no cyclic vector. Why? Let's consider. First situation, real space. Real space, then I claim that vector hx equal, for example, f minus x sine of x is orthogonal to any power of and so on. I take let f arbitrary function candidate on cyclic vector. So you construct all powers, and you can check that this vector orthogonal to any power. Why? Because scalar product looks like x to k f of x. This is akf. Then you put in scalar product f minus x sin x dx. So you see that this function is even. It's odd, so it is 0. So for any function, for any possible function, which you can take as cyclic vector, you immediately construct a vector which is orthogonal. So all powers, this linear span of all powers are not dense, because we have an orthogonal vector. But in complex space, for any function f in L2 minus 1, 1, what we can say? Scalar product will like AKFH, yes, it is minus 1, 1, x square f of x, h, we have a conjugation. So you can take h equal to f of x, then f minus x, and again sigma, sine of x. Square, that's square. Then if you put this in scalar product, you obtain x square f of x square, this on this. It is conjugation. Then f minus x square and sine x in dx. So again, this function is even. And again, this scalar product is 0.
Why we don't just take h to be f conjugate and sine?
In complex space, we have such scalar product with conjugation. If you take, you take this vector h of such type, then multiplication f on f conjugation gives us the square of absolute value of function f. It may be complex. This is real. This absolute value is real, so it is, doesn't matter on conjugation. And sine is a real function too, so that doesn't matter on conjugation. But for example, if you consider this vector, example 3, L2, 0, 1. L2, 0, 1. So the same operator, multiplication on x square. Then I state that function f of x identity 1 is a cyclic vector. So you find us here. Is cyclic vector. Because how you can show it? For example, equals to this system. And then you can use, for example, a lot of arguments why this function, the linear span on this function is dense. There are not all powers, or only even powers, but they are dense. Why? For example, you know that on the half in this space L2 minus 1, 1, we have a basis system sine and cosine. Yeah, sine Pnx, cosine Pnx and 1. But if you have a half of interval, half an interval, then you can take apart the half of system. It is a basis. Why? Because you, for example, you take any function from L2, 0, 1 and extended it, for example, as even function. Then in Fourier coefficients, all sine Fourier coefficients are zeros. So you obtain the Fourier series for this function only for cosine expansion on the whole interval. So it is expansion for the only on cosine. Taylor representation of cosine function have only even powers. So even powers are dense. Linear combination of even powers are dense in L2 on the 0, 1. Another argument. Mune's theorem. Mune's theorem is a very interesting theorem. It states, we know that, for example, for not formulation of Mune's theorem, what says for us Weierstrass theorem? They say that all polynomials are dense, for example, in space of continuous functions. But can we take not all polynomials, but only some polynomials? Lacunary sequence. Not all powers, but some. As here we have only even, for example. Mune's theorem says us for when it is dense in, for example, this space. If we numerate in the following order, then n1 must be 0, we must have constant. And then, second, this sequence have no large gaps. So lacunes are not large. For example, this is a good sequence because for this series is converged. But for example, if you take n square, it is bad sequence. The series converge. And for then, Mune's theorem states that linear span closure gives us a whole space. And L2, in L2, only this sufficient. It is necessary sufficient conditions. For continuous function, we need constant. But in L2, only this convergence of this series. So, or by these arguments or by these arguments, we obtain that one is cyclic vector for this space. Okay? So, what we can do with the cyclic vectors? Theorem, another formulation, another type of spectral theorem, as in terms of similarity. So and one more definition. If operator has cyclic vector, then it's named operator with simple spectrum. It is the same. The definition. If A has cyclic vector, it is A is operator with simple spectrum. It is a so-called simple spectrum, without multiplicity. We consider with example, for example, diagonal operator have cyclic vector if only lambda g are different. Diagonal elements are different. So it's simple spectrum without multiplicity. So it is equivalent notions. So theorem, let H is separable Hilbert space. A is self-adjoint and bounded. I consider only bounded situation. And A has cyclic vector. Then they exist measure mu on sigma of A and exist U unitary isomorphism such that the diagram is commutative, such that diagram, what diagram? We have our space H, we have our operator A from H to H, then you have unitary isomorphism U, L2 on spectrum with this measure, L2 on spectrum, this measure, here again U, and here we have new operator M. M, it is multiplication on independent variable. Mf of t equals t ft. So arbitrary self-adjoint operator with cyclic vector is equivalent or similar to operator on multiplication on variable, on independent variable. Okay? I don't finish the statement. Diagram is commutative. Commutative diagram means that A then U equals U then M. So this is a similarity of operators. So any self-adjoint operator with simple spectrum or with cyclic vector is equivalent, unitary, equivalent to operator on multiplication of independent variable. Again, examples from linear algebra. We have finite dimensional situation. We know that any operator, self-adjoint operator, we can find such orthogonal basis that the matrix of operator is diagonal. So we have multiplication diagonal. And measure is atomic measure. It is measure on the spectrum, and it is atomic measure only on eigenvalues. Another example, Gilbert-Schmidt theorem. We know that for self-adjoint and compact operators, there exist orthonormal basis that operator has diagonal form. Again, multiplication, but in L2. In L2 small, and again, the measure is atomic. The measure is atomic. But you can now, with the help of this theorem, you can describe the self-adjoint operators, for example, with the continuous spectrum. With continuous spectrum. So you can find such measure and such unitary isomorphism that operator is similar to multiplication on. If you have two types of spectrum, continuous and eigenvalues, this measure is atomic on the eigenvalues and continuous measure on continuous spectrum. On continuous spectrum. That is why the terminology continuous spectrum. So let's try to prove this theorem. Let x0 is cyclic vector. And we have a spectral function of A, of operator A E lambda. We constructed on the previous lecture, yes? This family of operators. Then you can define measure. I defined it only on semi-ring, alpha beta, sorry. It is scalar product in H. And this family is defined as follows. And then define unitary isomorphism U from our space H to L2 on spectrum with this measure. Construction of this unitary isomorphism. X0 goes to the 1. Ax0 goes to the T. It's independent variable. In L2 and so on. What happens with any power if it is isomorphism? Go to T, K. What we can say about linear span of all powers? It is dense by definition of cyclic vector. It is dense in H. We know, but we know that self-adjoint bounded operator, its spectrum lies in the interval. Yes, it lies on interval in segment, and the polynomial are dense on this soul and Tk from 0 to infinity. Linear span is dense NL2 this measure. So we construct unitary isomorphism. We don't check that it is unitary isomorphism, but it is very easy to check that it is unitary isomorphism. Why? Let's check it. So it's sufficient because it is dense set. Yes, it's sufficient to check unitary property only on dense set. So let's consider this. It is scalar product in H. We have an integral representation of operator A. We obtained the integral representation of operator A on previous lecture, yes? So we know that this is integral on spectrum lambda k plus n d e lambda x0 scalar product x0. We know that A equals to we have an integral representation. So we immediately obtain this. But this is our measure mu. So we obtain that it is lambda k plus n d mu. It is scalar product lambda k lambda n in L2 on spectrum with this measure mu. So it is unitary. Unitary operator. So is it clear? Yep. Not?
Maybe just repeat the
So again, our operator was a self-adjoint. We can see the bounded operator, and we have a cyclic vector. So then we know that any self-adjoint operator has spectral function in lambda. It's equal he minus infinity lambda of operator a characteristic function. We define it. We know that any operator has such a representation. Then I defined measure on subinterval, on semi-intervals. It is sufficient to define measure on semi-intervals because it is a semi-ring. Then you can continue it as character theorem. And this is additive function, so it is the real measure, and it is positive because it is equal e squared because it is projectors x0 x0, and it is self-adjoint projectors, so it equals it is non-negative function, so it is really measure. And then you construct unitary isomorphism. You take cyclic vector from here and say that u x0 equals to 1. 1 is constant function here. A x0 go to t. T it is independent variable in this space. And then by isomorphism, any power of cyclic vector is a multiplication, is a monomial, t powered k. It's monomial. Linear combination of these vectors, k equals to 0 to n. What happens with the linear combination? It is polynomial. It is polynomial because by our definition, it is our construction of this isomorphism is the result on the linear combination is polynomial. But this linear span is dense in H, and polynomials dense in L2. So we have isomorphism between all spaces. Full isomorphism from space H to L2 on spectrum with this measure mu. And then it is we construct this isomorphism, and then you construct only that it is unitary. When we have such representation of operator A, such scalar product on any powers, I check the unitary only on powers. But of course, it will be a unitary operator on linear combination, and then it will, and this is dense set. So it will be a unitary operator in whole space. It preserves scalar products. And here is, I check this, that it is really unitary. So we take this scalar product, operator is self-adjoint, I rewrite it in this manner. I put this power on the first argument. Then take this representation of operator, and any function of operator, we know that any function of operator, good function from Borel function, is function of lambda in this integral. So we have a powers of operator, so I take power of lambda, k plus n. Then d lambda and scalar product x0, x0. And by definition, it is just our measure mu. It's just a measure mu, by definition. But we have d, so d mu. And this is scalar product in L2. This is just a scalar product in L2. So these two scalar products are the same, if they coincide. So it is a unitary operator. So it is a unitary operator. Okay? But one example again. And then I explain what happens if operator has no cyclic vector. Let's consider such self-adjoint operator. Such self-adjoint operator. It is not multiplication on independent variable. Yes, it is multiplication on x square. So find measure mu such that A is similar to M, MHT equals THT in L2 on spectrum of operator with such measure mu. So this problem is clear what we must do. We must find the presentation of this operator as operator multiplication on independent variable, not on x square, but on independent variable. We need to find his spectral function. I think it was homework, not? We know that the spectrum of operator is 0, 1. It is values of this function. So spectrum of operator A is 0, 1, and it is continuous spectrum. So take lambda from 0, 1, it is here, and this is square root of lambda. So function E lambda acting on f equals 0 if lambda less than 0. It is if lambda belongs to 0 to 1, and it is identity operator if lambda equal or larger than 1. It is a family of projectors. For monotonic function, we discussed it again on previous lecture. And I take F0, identity is cyclic vector. It's cyclic vector. And so measure it is what we have. Of course, I consider situation when alpha beta lies in spectrum. So we have integral this is measure. This is measure. So in L2 with such measure, our operator is similar to operator multiplication of independent variable. Okay, and what happens if operator have no? I only just without proof we discuss it, but what we can do if operator has no cyclic vector? Self-adjoint, bounded operator, and A has no cyclic vector. Theorem. H is separable. Hilbert space. Then there exists decomposition of space H as H equals to direct sum of subspaces HK, K from 1 to n capital, And n capital can be finite and can be infinite. And operator A reduced on hk has a cyclic vector in hk.
For every k.
Hmm?
Is for every k.
Yes. Take it, theory without proof. The idea of proof is Zorn lemma on existence of largest element in ordered system. And if you know this fact, then you can obtain the following theorem that then theorem H is separable Hilbert space A is self-adjoint and bounded operator in this space. Then there exist measures mu k and u U is unitary isomorphism between direct sum of hk to the direct sum of L2 on the spectrum, but with different measure mu k. And such the diagram is commutative. What diagram? Here we have our operator A. Here we have unitary isomorphism U. Here we have direct sum of L2 spaces on spectrum with different measure. And here we obtain operator M. Here n capital. And what is operator M? M, if we reduced on some L2 on spectrum with measure mu k, f. It is t f of t for any function f belonging to the space L2 on spectrum with this measurement. So on each term, it is again operator of multiplication on independent variable. Okay? And again, the proof is repeating of previous theorem. Yes? We have, by this theorem, we know that this operator has cyclic vector. Then you take its spectral function and obtain the measures, mu. And construct u in any term as orbit of cyclic vector to the monomials. Yeah? And then combine it together. It's the idea of the proof of this theorem. So that's again examples, yes? That's again example. We can consider operator. What operator? Again, operator A, f equal x square fx, but in L2 minus 1, 1. Minus 1, 1. We know that in this space it has no cyclic vector. But what we can do? We can consider L2 minus 1, 1 intersected with even function. It's H1. And for example, L2 minus 1, 1 odd functions. It's equal to H2. In this space, we have cyclic vector in H1 for even functions. Even functions we take F1 is constant, 1. It is cyclic vector here. And here we take F2 x equals to x. And let's consider our parabola 1 minus 1. How looks like spectral function E lambda? We know that the spectrum is 1, 0, 1. Spectrum of operator is 0, 1. But you know that you see that it is multiplicity. You have two pre-images. So if we take lambda here, we have square root of lambda and minus square root of lambda. So we can describe E lambda on F equals 0 if lambda less than 0, because we have no spectrum. It is a characteristic function from square root of if lambda belongs from here to 1. And it is f of x identity if lambda greater than 1. So mu1 of semi-interval alpha beta equals to what? We have two symmetric intervals, but we integrate with constant 1. So it is equals and mu2 equals to what? You must consider the quadratic form on x, so it's x square. X square integration x cube. So x cube we have 1/3 beta minus alpha square root alpha, and we have twice, so it is 2/3. It is symmetric, so we must twice integral because it is odd function, yes? Even functions. It is even functions. So you can multiplicate your integral on 2, but this measure in this space, and this is measured in this space. And in all these spaces, this operator has cyclic vector. So in these spaces with this measure, it is similar to operator of multiplication on independent variable. And something how you can determine, for example, you have two self-adjoint operators. Two self-adjoint operators. How you can determine similar they or not similar? So in one space H, how you can determine similar these operators or not similar? Of course, they must have we know that this operator is similar. They have the same spectrums. The same spectrum. So spectrum of A1 must coincide with spectrum A2. Second, you can define measures by the function E lambda. So measure mu1 must be equivalent to measure mu2. What means the measures are similar, are equivalent? The sets of zero measure are the same. Measure are equivalent if and only if for any measurable set omega, mu1 omega equals to 0 if and only if mu2 omega equals to 0. The family of sets of zero measure are the same. And third, the multiplicity functions. Multiplicity functions. What means multiplicity functions? I tried to explain it on my fingers. So you have some subsets which lies in spectrum, and they are included. So n of A it's not n A1 and n is as index. N A of lambda equals to 0 if lambda do not belongs to the spectrum outside, and n A of lambda equals to G if lambda belongs to sigma G minus sigma G plus 1. For example, as a picture, let's consider operator multiplication of such function phi. Consider, for example, this operator of multiplication of this function phi. What is the spectrum? Here, all spectrum. But this part is twice, yes? It has multiplicity 2. So this set is sigma 1, and this set is sigma 2. It's sigma. So on this set, this sigma 1. Oh no, sigma 1 it's all spectrum, yes. And here, this part is sigma 2. So here the multiplicity equal to 1, and here multiplicity equal to 2. Okay? So we have this so-called unitary invariance of self-adjoint operator. Unitary invariance of self-adjoint operators. What it means? If all these three terms are the same, the two operators are similar. Okay. So I want to finish with the spectral theorem, and I want to discuss something on Fourier Transform because it's very useful. And maybe the last lecture on the next week we consider something for pseudo-differential operators. And to describe the pseudo-differential operators, we need Fourier Transform. So, do you know something about Fourier Transform? No. No. Artem, no, yes? So I need to consider something, information for Fourier Transform. And you studied for distribution too, yes? No, like this, yes. Artyom, is it correct for you?
R at the end.
R?
Yeah.
I just write formula and then we discuss for what class of function it exists. So, a new variable y, or this, I define this as dx is a Lebesgue measure, classic Lebesgue measure. It is so direct Fourier transform, but we omit this word and name it just only Fourier transform. And then you can define inverse Fourier transform. This. The difference only in this, signs in exponent. And don't think about inverse Fourier transform that it is inverse operator. Sometimes it is true, but sometimes it is not true. The question, for what class of functions you can define it easily without having arguments that integrals are exist. For what class function you guarantee that integral exists, the Fourier transform exists?
Compact support.
No, it is not interesting. It is not interesting. Local integrable it is not good because you integration on whole axis. I consider only one-dimensional situation because you can consider Fourier transform for functions of many variables, but all results approximately the same, but the technique is more difficult for problems. Schwarz space is good, but it is not very large. But it is good. Yeah, of course, we consider a Schwarz space after two theorems. But first theorem for any function, for integrable functions. You write integral. So your function must be integrable. In what sense? In Lebesgue sense, in L1R. So theorem. If it's integrable functions in absolute values is construction of Lebesgue integral, and this is continuous functions. So what is the functions? G continuous and g of y tends to the 0 as y tends to infinity. Function vanished at infinity. Function vanished on infinity. Proof of this theorem. First, let's prove that continuous. Why Fourier transform is continuous function? Because function which is here is continuous function on parameter y. Because exponent is continuous function. Yes? And This is continuous functions. So I suspect that you don't know about Lebesgue theorem, Majorant-Lebesgue theorem. No? No? I formulated what it means. I formulated just for this situation. Let's you have function of two variables, and y belongs to some set omega, number set. And what happens for any y from omega is measured by this function, which is from L1. And for f is continuous for any x in R, f continuous in omega, in parameter y, in parameter continuous, then is continuous function. So you have Majoranta for all y's, and for y's you have a continuous function. Then integral on R is continuous function. It is variant of Lebesgue-Majorant theorem. And by this theorem, you immediately obtain this continuous function. So we immediately obtain that f with hat is continuous. Is continuous. So why this property is valid? Why it goes to the zero? Why it goes to the zero? Let's again what we can do. If we consider two functions, second. Then you can write this estimation, and this is just the norm of this function in L1, yes? And then you immediately obtain that if Fn goes to f in L1, then the Fourier transform goes to Fourier transform uniformly. You have no parameter y here, so it is valid for any y. This estimation do not depend on y. No dependence on y. So you immediately obtain that it converges uniformly. And third, let's function f is characteristic function of interval AB. We begin Fourier transform.
Yeah, thank you.
Can you calculate the Fourier transform of this simple function? It is indicator of it. what happens with this function as y goes to infinity? Imaginary exponent is bound.
Zero.
It go to the 0 as y go to infinity. And we have no problem at 0, by the matter. We divide on y, but there's no problem in 0, because it is 0 at 0. It is no singularity. It continuous function. But what we can do with the indicators? Any measurable function can be approximated by the linear combination of step functions. So it is can be approximated by linear combination of characteristic function. If f belongs to L1 on axis, then exists Fn linear combination of characteristic functions. So for characteristic functions, we know that it tends to the infinity, yes? Because for one function. So for any finite linear combination. And these functions uniformly go to this function. So we have this property and we have this property. Okay. So we immediately obtain that this function belongs to C0. And again, in second step, we obtain additional information. It is bounded operator. It is bounded operator. This is what is the norm in C0. What is the norm in this space? Norm in this space is supremum of values of functions for all parameters y's here. So we can take here supremum, but these do not depend on y. What is the estimation for the norm of operator of Fourier transform? If we consider it from L1 to C0. It is not less than this. No. And I write, I know that in physics, Fourier transform defined without this factor 1 over 2 squared to p. But inverse must have factor 1 over 2 pi. But I won't consider symmetric situation, because for symmetric situation we prove that this operator is unitary in L2. It is unitary operator in L2. And with Fourier transform we have a good instrument to calculate the spectrum of operator. So it is clear, yeah? But it is not good operator, unfortunately. Some properties of operator. I write it without proof, but properties following. Is in this situation. It is injective. Maybe if we have time, next lecture I will show how to prove this. But second situation is the range of operator is not all space. There exist some functions for which are not the image of Fourier transform. The range of operator is not all space. So in these spaces we can't consider the inverse operator, because by Banach theorem the inverse operator is unbounded. I can construct, I can formulate some sufficient theorem, and we consider that it is not the space are not good for us. Do you know what means Dini condition at point? Dini condition at point. Oh, how Dini? I think it's. Artem, do you remember how Dini written? Is it? Dini condition at point. x. For any epsilon positive, there exists delta positive, such for it is like a smooth condition of existence of derivative in integral sense. It is a derivative. Oh, sorry. Yes. It is a derivative at point x. Approximately. Yes. We have this ratio. If we take a limit as t goes to 0, we obtain the derivative if function differentiable. But function function may be not differential, but we have this property, for example. Then we say that it is a Dini condition at point x is fulfilled. And theorem is following. Let f belongs to L1R and at point x, Dini condition is valid. Then you can reconstruct the value of function f at x at this point with the inverse Fourier transform. With the inverse Fourier transform.
Only if this condition is satisfied.
If this condition satisfies. And moreover, the integral in the principal value as a Cauchy limit, principal value, symmetric. We go to infinity in symmetric way. For arbitrary function from L1, we cannot reconstruct the value of function in point x with the inverse. Because, for example, what you can say here, let's consider he AA. What happens if we consider symmetric? It is minus AA, minus AA. It is A, so we have, it is B, yes? So we obtain E minus AY minus EAY. So it is equal to minus 2I sine AY. Yeah? And if you put here, so we obtain this Fourier transform equals 2 sine AY divided on Y. It does not belong to L1. It does not belong to L1. Because absolute value of sine is not an integrable function. Divided on Y. Only one power. There's not an L1. You can't calculate the inverse Fourier transform to this function.
This one, L1 is...
It's not an L1. It is not an L1.
L1 is such that the...
It's an integrable function on all real axes in absolute values.
Absolute. Ah, okay. But without the absolute, if this integral is without the...
Without absolute values, yes, by Dirichlet conditions.
Okay.
Not Dirichlet conditions, no, yes, it's by Dirichlet property. Y goes to the 0, monotonical, 1 over Y, and all primitives of sine are bounded. then there exists the integral of multiplication of two functions. You have f of x, g monotonically goes to infinity, and primitives of function f are bounded. Then exists integral of multiplication of f of g. Okay, so it is 1 over monotonically goes to infinity, and these have bounded primitives. So without absolute values exist. But in L1 we have functions which must be integrable with the absolute values. And so we obtain that f L1, then f belongs to the 0 R. It means that f of y equals O small o 1 as y goes to infinity. Yes, we can interpret this C0 as following. C0 is a continuous function which vanishes at infinity. The limit at infinity equals to 0. In definition, with norm supreme, since it's Banach space.
What is that? 0 bar delta.
What?
Is this
0 vanishes at infinity.
no below that? Is it 0 bar f cap y?
It's O small. It's
0.
O small. Symbol O small. It is the same as. It means that f y goes to the 0 as it is the same. It is so-called O small. Do you know? You don't know this notation? O small, O capital. No? No. How you integrate? How you live without this? So it's just a definition. And now two additional theorems which explain us something interesting property of Fourier transform. Two questions. Can we say something about smoothness of Fourier transform? And can we say something of the velocity of going to the 0? We know it goes to the 0, but only this estimation. Small. Special for you. Two functions, f, x, and gx. You say that f equal O small of g bar, you want to show that it is O small, not capital. O small, it means that lim f on g as x tends to x0, for example. X0 may be infinite, finite point or infinite, yes, equals to 0.
F by g.
F equals O small of g if this. So in here you write this f y divided on 1 and goes to the 0. Okay? O capital of g, that means they have approximately equal growth. Have two-side estimations. For example, sine is O capital of 1. Yes? So theorem 1. Let f belongs to L1 intersected with C1. So it has one continuous derivative. And this derivative belongs to L1 too. Then f hat So it decreases faster. Yes.
Here is jet.
He's only O1, O small of 1, and here O small from 1 over y. So you have more precise information on it decreasing. It decreases not as.
But should not depend of L. If it's smooth, the function is more smooth, it should decrease faster.
Yes, its function is smooth. The more larger function smooth, the larger Fourier transform go to the zeros.
But why is not this don't depend of L? This O.
It is y is the argument for the Fourier transform in my notations.
Yes, but this O, this should not depend of L in some way.
What L?
L, you mean the F?
F belongs to L1
Intersection with C.
with C1.
C1.
C1, one derivative.
I
Intersected with C1 here.
CL. Okay, C1.
C1. It is a function with the continuous derivative.
Continuous, okay.
So how we can prove it? It is easy because we know by definition that Fourier transform is the following integral. Let's continue here. Put the exponent inside the differential and then integrate by parts. Don't worry about zero because we want to obtain the behavior of Fourier transform for the large y's, for the large values of this parameter. So we have no problem at zero. We can integrate it by parts. We can do it because our function is differentiable. Our function is differentiable, and this derivative belongs to L1. So this integral exists. All calculations are valid. Yes. What you can say about this integral? We know that Fourier transform is O small of 1. So it is equal to O small of 1. So with this, it is O small of 1 over y, because we have this. What you can say about this? It's for parameter x. For parameter x. Why the limit of function f is 0? No. You can construct example of function of L1 which have no limits at infinity. The integral, the limit of integral at infinity is 0. But function
no.
Function no. So consider such example. n plus 1, here 1, here 1, but this this is point n. This the length of these intervals go to 0, such that integral exists. So Sn plus 1, the length was such that the sum of Sn is finite. Then function belongs to L1. Because its integral on all axes is just up to the constant 1/2, the square of the triangles. The integral equals to this Sn, yes? So function is from L1, but it have no limit at infinity because this point is 1 and this point is 0. But what bad with this function? If you take this interval smaller and smaller, the derivative increase. Derivative increase. But here we have property that our derivative belongs to L1. Derivative below. That's why this goes to 0. I just prove it more strictly. Why? How we can do it? A function is differentiable. So you can write Newton-Leibniz identity, yes? So you can write f of x minus f of a equals from a to x f prime t dt. Yes? And this function is from L1. So it have a limit, exists limit for x goes to plus and minus infinity. These functions have a limit. And this limit f plus minus infinity equals a plus minus infinity f of t dt plus f of a. Yes, because derivative belongs to L1, we have a limit at plus and minus infinity. What is the value of this limit? Your function is integrable. So the limit must be 0. Because if your function stands to some not zero number, this value is infinite. So integral is infinite. So if its function is not integrable, so it must be 0 for this property, function from L1. So we immediately obtain that it is 0. So we see that it is have a good decreasing, and by mathematical induction, what you can prove? How you can generalize this theorem? For Ck, and all these derivatives belongs to L1 from G. I take away something. G equals 0, 1, K. Yes? All these derivatives. Then your integration by parts. By integration by parts. So it is clear, I think, yes? We don't discuss it more precisely. By integration by parts, you can obtain this the formula. So I think it's time to make a 10 minutes break.